Hello and welcome back. In the second part here, we want to look at a more advanced approach, how we can use clustering methods. Before, we had used the manual threshold or k-means on the hardness values themselves, or looked at how we combine the two to clean up, and then used the B-scan to find individual clusters. Now we load the data again, define this value and look at the plot again, and we remember that we had a lot of artifacts that we want to take care of. And our case was that we wanted to discriminate between the martensite and the ferrite phase, and if we just use the k-means, we found that we only had two classes, but all the artifacts are then part of the ferrite phase, which clearly isn't the case. Now when we look at this, it's obvious where this goes wrong, but in computer code we need to look at this a bit more different. So how can we use more advanced approach? So the idea here is that we define a hardness metric on a given set of points. So the difference between those 2 points and those points, and then take the square root of this. This is how we define a custom metric based on the hardness. So essentially we have a point x and a point y, each have a coordinate, and they have a hardness value. So this is how we, if you want, represent each of the nanoindentation dots as a vector. And then what we can do this is we take the length of that vector. So what we can do is we have our data frame of x and y position and the hardness. So this is what we measure from the nanoindentation. And then run the B-scan, but now we give it our hardness metric. So the idea of using this custom metric is that we don't use the hardness values to cluster as we did with k-means, where we have the distribution of the hardness values and cluster the distribution of hardness values, but that we use the x and y position here and use the difference in hardness between neighboring points to discriminate between the different phases. And that should, at least that's the approach that we want to pursue and test, that should also allow us not only to discriminate between the martensite and the ferrite phase, but also all of these artifacts. And that is because the reasoning behind it is that we have, well, if we have one phase here and another phase here, there's a fairly big difference in the hardness, but we also have these regions that are very different again. So the clustering algorithm should learn that these regions indicated by this color should belong together, these regions that have similar colors here should belong together, and then there are these artifacts that are different from both this region on the martensite and from the ferrite region, and they form their own clusters. So this is what we want to achieve with the custom metric, and this is what we encode here. So when we run this sort of works. We can see that here we have the artifacts, so we have a lot of clusters. The algorithm has found the martensite in the ferrite phase, and well, the artifacts marked back. Now we have 23 clusters. Let's first improve this a bit. So we employ some standard techniques by scaling and normalizing the input data frame, right, and tune our setup. And if we do that, that looks a lot better. Then we only have 5 clusters, right? So we have the martensite phase, and we have then the different artifacts and the big ferrite phase. So this is a lot better. We have many fewer clusters, and each of the phases is essentially in one cluster that you can see it's indicated by the color. And you can see that it's not perfect everywhere, but essentially we've achieved our goal by normalizing and scaling the input values, that these regions belong to the martensite phase, these regions belong to the ferrite phase, and we have regions that are distinctly different. These are our artifacts. And so we can now plot this. Everything that's not one of these clusters is then also noise, so we can look at noise and artifacts, and we can see that this is indeed what we also would expect from our electron microscope image.
We can plot the different phases, so we can plot the martensit and ferrite phase, and you can see that we have a homogeneous distinction between the martensit islands, almost like there is some noise there, and the ferrite phase. You can also then look at the artifacts and the noise again, so we see that all of the dots that are in the phase here that are missing, these are clustered as noise, and we have those bigger artifacts, so we can cluster on all of those again. Then we still have all the noise, so this is what we could, for example, then remove and clean up from our data sets, and we have found and identified our artifacts where there are some holes you see underneath the material. And then we can also then look at what is the average hardness in the cluster. And we can see that they're similar but not quite the same. And we can do now the same thing for the clusters in the martensit phase. Right? So we first isolate everything that's classified as martensit and then find all the clusters. And now we have all of those, and we can see that these small regions are identified as noise. And now we can do the same thing that we have done before and say, okay, how does the hardness vary across the various martensit islands? And we can see that within the uncertainty it's quite homogeneous.